All right, so here we are going to look at a very simple two-layer network. One reason I may have initially tried to kind of breeze over a discussion of the data set is because the way that we build our data sets in Keras is going to be a little bit different than the way that we build them for the NumPy example, okay? So we're still going to need NumPy because the TensorFlow API takes NumPy arrays. We're going to need to import TensorFlow as TF, right? And again, that as TF bit is going to be so ubiquitous that like a lot of places just assume it. We're going to always do it. And then we're going to import TensorFlow.Keras as Keras, right? Then I'm going to build my inputs and labels. So when we were working with NumPy, a convenient way to do that was to create a list of tuples of input and label, right? For Keras, we are going to package our inputs in a two-dimensional, in this case, array, where each input is a row, okay? In Keras, each input is a row. And then I'm going to package my labels in another array where each label is a row. I need to make sure that these two arrays are the same size and that the rows match, right? That the first row has the first sample, and then the first row of the labels has the first label, right? I need to make sure those match up, right? So, rows, row-wise. And then this block builds my model. So again, we're not going to be writing explicit matrix math now, right? We're going to be working in terms of high-level classes like models and activations, right, that describe our network. So here, I'm going to construct a Keras.sequential, which is a basic feed-forward model, and I am going to give it a list of layers, okay? A list of layers. Each one of these things is a Keras layer. So the first one is the input. This one, I believe, is optional. If you don't include it, Keras will assume the input of the bottom layer based on the first input you give it, right? I always like to do it just because I like to be explicit and clear. So here I have two inputs. Dense is your plain old bargain basement wx plus b layer, right? It has a weight matrix and a bias. Keras will figure out what sizes those need to have, and if we don't specify it, Keras will use intelligent and reasonable initializations for these, right? So we don't have to write any of that. We just say we want a densely connected layer that is 5 wide. This activation is an activation function, right? And then another dense layer, an activation, a dense layer, an activation. So this code right here, just this, completely defines a 3-layer, no, actually, yeah, sorry, completely defines a, would it be 3 or 4 in the terms we were using? Yeah, it'd be 4 in the terms we were using, right, because that was kind of the input. Completely defines a 4-layer network, right? If I were drawing it, it would look like this, right, 2, 5, 5, 1. And I'm not going to draw all of the connections, right? So, think about how much work you had to do before, even with a code sample in front of you, to add a layer, right? Because I asked you to take this network for the homework take this NumPy code and add a layer to it, right? In Keras, building a network that has that extra layer and is also wider is this easy, right? We just describe the structure from input to the weight layers to output, and we list the activations. Yep. Oh, right. And so, yeah, just to state clearly, the dense layers and activations have to be paired, right? It should go weight mult, activation, weight mult, activation, weight mult, activation, right? You don't have to. You could do it in other combinations. This is the only one that really kind of makes sense right now, right? You could have a bunch of weight layers in a row, but there actually wouldn't be a reason to do that for linear algebra reasons. You could have a bunch of activations in a row. I can't think of a time when doing that is useful. Like, they should, in general, be paired like this, right? Weight layer, activation, weight layer, activation, weight layer, activation. Okay. So we need to call model.compile after we define it. That will compile our model. It also allows us to specify our optimizer, right? So if you're wondering where the stochastic gradient descent algorithm we used before lives, it lives right here, right? We specify our loss. There's where our loss definition lives. And then we can perform our entire training loop right here, right? After we compile our model, model.fit, give it that 2D array of inputs, 2D array of outputs, and tell it how many passes through all of that we want, and it will just do it. Our model is callable. So after we have fit our model, we can just give it a NumPy array of input, and it will tell us the output, right? And I only had one row here, but we could keep giving it several rows, and it would give us several rows of output. So I couldn't get all of this text on one slide at a time, that's why I kind of did it this way. I will post this code so you can look at it, but here, it's very short, very straightforward, and I think very easy to change, right? And there's our complete little sort of like dense, right? Relatively, I shouldn't say dense, just say deep. Relatively deep, right? Because I built a network right, that had two hidden layers, right? And am training it on, and I'm being bitten by my cat, and I'm training it on, what rule did I use? XOR, all right. So, yeah.